welcome back. Today's video is going to be about the advanced features of the R programming language. So I'm going to be talking about conditional statements, namely if statements, for loops, while loops, nesting loops, and there was another one too, writing functions. Okay? So I changed around the RStudio layout to make writing the more complex code easier. On the left, I have a R script that I'm going to be using to write out the loops and everything, because I need to be able to add spaces as necessary. On the right here, it's the console where the R code gets run and the output's created. And down at the bottom right, it's the environment. Okay, with that, I'm going to get started with if statements. So if statements are conditional statements that only run if the argument in the if parentheses evaluates as true. Okay, so I'm going to go ahead and get started with that. So I'm going to say x equals 5. Run that. And we have down at the console x equal to 5. So if x is equal to 5, and that's double equal, we print nothing. One of the least complex things to do is print. So equal to 5. And I would act like I was in the console and hit enter when I couldn't have. So you see in the console it returns equal to 5. And if I change that to 4, it will run and do nothing, because that statement did not evaluate as true. Okay? We can do that with a different conditional statement. So this is if x is not equal to 6, and of course x is 5, so it's not equal to 6. Print. I'm going to shorten it because it's not really necessary to write the whole thing. And that ran because it's a true statement. Okay? We can also make if statements without parentheses. So equal 5. And I can just do print equal 5. That runs. I don't like it. I much prefer the bracket so I can see exactly what is in my if statement and what is actually not in my if statement. But that's something you can do if you want to. Oh, and in that system, it has to all be on the same line, which makes it more difficult too, because you can't do more than one thing unless you do something like this, add a semicolon, and then do your next thing. Print extra stuff. So if I run that, it will do it, but if I put that on a new line and run it, it will only do that one thing. I'd have to put it in all in brackets here to make it do both things. And this is by far my preferred method. But it's a matter of preference, not necessarily right or wrong. Okay, I'm going to go ahead and clear my console and get back to the code in the book. Okay. So now we have a double condition if statement. So, and length of x equal 1. Then we do that thing, which would be print. Oh, I gotta have quotation mark. X is a single number equal to 5. Okay. And if I add a number to x, okay, now x is not a single number but a vector, and I run this line of code, it's really mad at me. Yeah, because I'm trying to run this condition right here, and it's looking for a single number, not a vector of numbers. So that actually won't even run, but it still shouldn't run anyway. Let's do something kind of weird and just subset that, so it won't throw an error. And okay, now that it didn't throw an error, it just didn't produce any output because both conditions were not true. Okay, and now I'm gonna set x back equal to 5, because I think my subsequent code depends on it. Okay, so we have an OR statement. So the OR option's a little bit weird. It's that straight up and down line that perhaps on your keyboard is right under the backspace. You just have to look around for it. I don't have any better advice than that, unfortunately. Okay, so 5 equal to 5, which is always true, of course. And I need to go back and change this other block of code. Okay, so x equal to 4. X is not equal to 4, of course, because it's equal to 5. And when we run that, it still evaluates as true because we have the OR. And if the second piece always evaluates as true, so that's always going to evaluate as a true statement. Okay? Now we're going to get into while loops. And the while and for loops are the real reason I switched to the R code block system, because I need to add spaces, and typing in the console does not really allow that very well. Count equals 0. So every time the loop runs, we want to count up 1. I'm not even sure what we're doing yet, but we definitely want to count up 1. Okay. So while this counter variable we just made, make sure you adopt the same capitalization of a bad habit of doing lowercase and capital counters. Okay. So while counter is less than or equal to 5, we print the counter. And then counter equal counter plus 1, and I made that mistake where I capitalized counter, and it shouldn't be. Okay? So we're going to get this output where it says count from 0 to 5. The first loop is 0, print 0, add 1, next loop is 1, add 1 to 2, and so on. And it will continue running while this counter variable is still less than or equal to 5. So of course it's important to make a condition that will eventually evaluate as false. If you don't, you're going to have an infinite loop. A very easy thing to do. And actually I'm going to make an infinite loop just to show you what you have to do when you make an infinite loop. Okay, so while... How about we use that other variable? X is less than or equal to 5. This will never evaluate true, and it will be an infinite loop. So when you make an infinite loop, you're going to keep going on forever, and what you have to do is hit stop, and hope your R session's not been impacted. Okay, so it's printing. That's a good sign. And let's see if this whole thing just worked again. It does, okay. Sometimes when you make an infinite loop and stop it, you need to go in the session and hit restart R. That wasn't true this time, but it will come up. Okay. Oh, so now we're doing, I believe I make a plot for this. No. Okay, let's see what we're setting up. Okay. So we're doing a while loop that sample from a standard normal with increasing sample size, and we'll see how long it takes to get to a sample that's close enough to the population mean. And I lied, it's not a standard normal, it's a normal distribution with population mean 1 and population standard deviation 1. Okay. Let's get started with that. And hopefully I'll have enough space. Okay, so we want a sample that gets within 0.001 of the actual population mean of 1. Actually, I'm going to go ahead and write these all on the same line. With just assigning variable that won't change. And I want enough space to write all this code before I get too far down in my head covering the code. Okay, and then that's 1. Okay. And now we have that same counter variable equal to 0, diff equal to 1. The diff equal to 1, that's the initial difference between the population mean and the sample population mean. We started at 1, so the while loop doesn't either immediately evaluate as true because it's too small, or it doesn't not find a value for diff and refuse to run the throw an error. So we had to set an initial value that allows the while loop to run, and it doesn't immediately evaluate as false. Okay? Okay, now we're getting closer here. So we're going to make a string of numbers. I'm going to try to adopt the same capitalization. Okay, so we have one value from the normal distribution with mean equal to the population mean variable we set, and standard deviation equal to the population variable we set. Okay, so that can be one value. And I tried to run that and it wouldn't run because I didn't run the stuff before it. Okay, now it's all happy. Okay, now we're going to start the actual while loop. So while this value diff is greater than my desired difference of 0.001, the counter goes up by 1. Just to keep track of how many times the value runs. The difference is evaluated. So the difference is the absolute value, the difference, the mean of the variable number string we created, minus the true population mean. Okay. And then if the difference, is less than or equal to the desired difference, print counter. That this is only going to run one time when the difference between the mean of the vector we're creating and the population mean is below that threshold of 0.001. Okay? And then we're going to add an extra value to the number string. Our norm 1, comma, pop mean, comma, pop SD. Oh, that's mean again. That doesn't matter because they're both equal to 1. But if we were to change the numbers, that'd be a problem. Okay. So what we're doing is we're finding the length of this vector required to get a sample mean sufficiently close to the population mean to we're estimating the sample size necessary. Although this isn't a perfect test, this is really just a demonstration of using a while loop. So we're running the loop until this condition is met. It won't be too long. So in this run, it took 3,628 samples before we got a value close enough to the real population mean. I'm going to go ahead and do that so we can see what we actually ended up with. Okay, so we have mean and the number string, and we actually want to take off the very last value because that was added after the mean was evaluated. So it didn't really go into the calculation. Okay, so what I did here is I said I want the mean as a number string minus that very last value, which happens to be the same as the length of the number string. Okay, so we got a mean of 0.9991, which is sufficiently close to the population mean. And if we keep running this, we'll get different values over and over. That one only took 129, 56, 442. Oh, that was only 14. No, it's random, as you'd expect, if we're sampling random numbers from the normal distribution. And the real point here is that it's what the while loop does. It runs the block of code until a certain condition is met. Okay. And now we're doing a slight variation of that. We're running until a certain amount of time passes. So run time equals 15. Counter equals 0. We're getting the start time that comes from the operating system. So proc.time, and we want the third element. I'm going to go ahead and run it in the console to show you what we're dealing with. Okay, so when you run proc time, you actually get 3 different times. the user time and the system time might be useful in some instances, but what we really want is the elapsed time. And we're going to take the difference between the elapsed time at the start and the elapsed time at the program's running. Okay. And before we start the code, the elapsed time is equal to 0. That's pretty uncontroversial. So while the elapsed time is less than or equal to the run time, keep running this code. So I calculate the elapsed time equal proc dot time, and then once again I want the third element minus our original start time. Okay, and then we need to actually do something. Theoretically we wouldn't have to, but it's nice. Okay. And I don't know why we're adding 3 exactly. Operation 3. I'm sure I explained it in the book. Don't really know right now. But, okay. So this is going to run for 15 seconds. And maybe I can try to figure out why it says 3. Okay, I have no idea why I said 3, but that doesn't really matter. Let's keep moving on. Operation per second. Alright, runtime. Okay, and then we're going to print it. Okay. Okay, so here we got a lower number than I did before. So my single core performance on this computer is probably worse than my main computer. Okay, now we're going to move on to for loops. So I'm making a list. Not really sure why I called it list. Because a list is a specific data type. Hopefully it can be more clear to me in a minute. I should have called it factory. So for I and list, so what we're doing is we're picking the variable we want to change in the for loop, and we're saying for each, and we're telling it to change for each the value of the list. So here I don't put list, I put I. So for the first time it runs, it's going to take the first element out of the vector and print that. The second time, it's going to be the second element, and so on, until all 5 elements are printed. Okay, and we see that in the console right here. And it looks like I'm doing a new simulation. Oh. Okay, so we're going to be looking at maximum and minimum value. The list, our norm, 1,000. So we're sampling 1,000 values from the normal distribution. Okay, so we need to make initial value for the minimum and maximum. And these initial values is just going to be the mean. So they're definitely not correct. The mean can't be the maximum and minimum unless it's all the same number. But we have to make an initial value, or when R tries to refer to the value, it's going to see that it's missing and not know what to do. Okay, and the value should be close to 0. Maximum, minimum, yeah. A number really close to 0, as we'd expect from a standard normal. Okay, so now I'm making the for loop for I in list. So the value of I is the one that changes each time the loop runs. And the value of I takes different takes on a different value every time you take one element from the left. So if I is less than the minimum, we're going to make that value of I the new minimum equal I. And then after we go through every element of the list, whatever is left would necessarily have to be the true minimum. And if I is greater than the current maximum, we're gonna make it the new maximum. And I want my output to be minimum, comma, maximum. I'm going to run all the code. And I get the value. We didn't actually need to do that. The min list and max list. We take the exact same value, and we do. Okay. Alright, let's do the next example. In the previous video, I talked about the apply function and how it applied a function to either the rows or columns of a matrix. And we're doing that again, but with a for loop. Matrix, our norm, 100, in row equals 10. And I can stop right here and it'd be fine. But I'm going to go ahead and specify in column equals 10. It was not necessary, but it could be explicit. Okay. So now we have a matrix of 10 rows and columns filled with the standard normal distribution. Okay. So I'm going to make an empty factor of mean here. So rep 0, 10. So that's a factor of 10, 0. Right here, 10, 0. I'm going to go ahead and clear the console. Okay, now I'm going to actually make the for loop for I in 1 through 10. Okay. I could also make that 10 be read from the matrix as in column or in row. I'm actually not. So, yeah, we're doing a column. So I could say in call here. In call of Matt. It doesn't matter. I'm I'll go ahead and stick with that. So, why did I do that? There we are. I think I did the parentheses. I'm so used to doing the parentheses with mean. But of course, I'm allowed to make that variable name because the function is mean, not means. Mean met comma I. So that's the mean of the first column, mean of the second column, mean of the third column, and so on. Okay, and that's actually all I had. So I want to return the mean, and I want to demonstrate that I did the same thing. The apply function, mean. Okay. Or I could be more rigorous with it and do mean equal apply met comma 2 comma mean, and sometimes it won't evaluate as true when it is true due to our rounding. This clearly should be true, and yes, they do all evaluate as true. Okay, so the benefit of using in color here is that I can change the dimension of the matrix. So if I wanted 12 columns, I don't have to go back down and change my 10 to a 12. My code knows that I changed my 10 to a 12. And no error. So I probably would actually do in call mat instead of 1 through 10. It doesn't practically matter, but when you're making changes to your code upstream, you gotta think about what happens downstream. Okay? And I'm doing another simulation. What is this? Wait. Oh. I got ahead of myself and did in call instead of what I did before, so that's the same thing. Okay, now we're talking about nesting loops. I actually don't need to get rid of that first line. I'll go ahead and put that back to 10. And clear the console. Okay, so I'm doing mean dot numeric apply met comma 2 comma mean. And the reason why I would do add.numeric here is because what comes out of the apply function isn't necessarily numeric, and this forces it to be the correct variable type for the mean function to be applied to it. Maximum is going to be the same thing. Maybe I should just copy the code, but I'm already typing it, so. Mat, comma 2, comma mean. Okay, so look, this time we're finding the maximum and minimum values in a matrix instead of a vector. And that's why we need a for loop. We need a for loop to iterate through the rows, and we need a for loop to iterate through the columns. Oh, and I almost made a mistake. I want that to be 100. As many times as you can set parameter values in the beginning of your code and have them propagate down, the better. Because I almost made a mistake right here. A lot of times when I'm writing code myself, I would do n equals something, p equals something, or norm equals n times p, in row equals n, in call equals P. And if I ever need to change the number of rows or columns, I change the variables up top, N and P, and the rest of the code propagates down. So I in 1, 2 in row. So I'm not telling them how many rows I have. I just want the code to figure it out. And then I don't have to indent the next for loop. It's a very good idea, but you don't have to, not like Python. In call mat. Okay. And now we're doing the same thing here. If mat I comma stay, so we're saying we're updating the matrix that every value of I and say, or rather every combination of I and say. So I and say 1, 1 all the way to 10, 10. All 100 elements of the matrix. Oh, and I got distracted, so minimum. Yeah. And then minimum equal mat I comma say. So it's not all that dissimilar from when we did this exercise with one for loop, but now we're just doing it with 2 for the rows and columns of a matrix. Greater than maximum. Maximum equal mat I comma say. And here we are. P minimum comma maximum. Ooh, why did mad? What did I do? Numerical expression only has 100 elements. Okay, so it only got mad when I got to the loop. That's what I did. I said call, not in call. So a little mistake like that will make your code go off the rail. Okay. That's a very reasonable answer. And similar to this one. Let's see if we get the same answer using the apply function. So minimum of apply mat, comma, 2, comma, min. Yep, okay. And then, gotta make sure I get the brackets right. Believe that's right. Mat, comma, apply, comma, mat, comma, 2, comma, max. Okay. And it didn't matter which way we did it, we got the same answer both times. Okay. Not 100% sure what we're doing, because I didn't read my own book ahead. But let's go for it. Okay, the max time equal to 1. Resolution equal to 5. Operation rep 0, comma, resolution, time, max, time. Okay, so this tells me we're going to have 5 data points. If we have 1 times 5, and we have counter 4. I guess it's the counter for the for loop. I want to make this block right here its own variable. Okay, the I sequence. 0.01, comma, max time, comma lanes, dot out, equal resolution times max time. Okay. And you got mad at me because I didn't run all the code before it. Oh, and it's still mad at me. Okay. What the heck did I do? Yes. You heard it here first, folks. A random day will break your code. Also, not highlighting all your code will break your code. Okay. Now we have everything we need. So, for I in the sequence of sequence of values I will take. So we have the counter going up again. I love a counter. And it's good. Okay, so what the heck am I even doing? Okay, so runtime will equal I. Oh, I see. So this sequence is the sequence of runtime for this program. Okay. Start time equal the proc time, proc dot time. That one hard bracket. Okay. I remember what we're doing now. We're looping through and essentially doing what we did before. We are running the computer for a certain amount of time and see how many operations we're able to execute in that time. So we're going to make a little plot of the time allotted for execution compared to the number of operations run. And elapsed time always needs to be 0 before we do anything. 0. And then we have a while loop. That same while loop we had before. Now it's in a for loop of different run times. I'm going to make an extra space between this while loop and this for loop. That's to help readability. So elapsed time equal proc dot time. And there's no argument to that function. That's why it's just blank. And we want the third element of that output. Minus start time. Okay, and just like we did before, we do counter equal counter plus 1. Did I notice something I missed? Counter equals 0. Okay. And that's why I did counter 4 outside the for loop. Because I can't use my normal word counter, because that counter is for the inner while loop. Just like you can't have the same indexing variable in nested for loop, you can try to keep your counter separate for the outer for loop and the inner loop. Or for any loop, I guess it really doesn't matter if you have a for loop on the outside or a while loop on the outside. You should always keep separate counters, or your counter is going to count up every time an operation you don't want counted in that variable counted will be counted. Okay, and I'm doing 3, and I really don't remember why, but that's what we're doing. Okay, so that's the end of the while loop. And then down here, underneath the while loop, we're doing operations. We put in counter 4 with the number of times the for loop iterated. So counter 4. And that's just going to be the counter. In the while loop, which is simply a measure of the number of operations that were executed while that while loop was running. Okay, so we're going to have a vector of operations that depended on the execution time. And we're finally getting to something. So, while. Oh. And also, your for and while loops should not be capitalized. Alright. And now it's running through each execution time. And now I'm going to go ahead and plot this. Okay, so what I wrote right here is actually a variable called iSequence. I don't need to worry about writing that whole bit out. iSequence and operations. And we'll talk about it. I'm not going to bother labeling the active. Okay, so we get exactly what we got here. Except the numbers are smaller, because my single core performance on this computer must not be as good as the other one. Okay, so we had almost no time, we got almost no operations, more time, more operations, and so on, and it's just about linear. Okay, now to the last topic I'm going to be talking about in this video, writing functions. And environment. Okay, so writing functions is going to be a little different, but not really. There's only a few ideas we have to get across. Okay, so you write a function by typing out the word function, and in the parentheses you add the variable or argument you want in the function. So the only argument in the function I'm making right now is the list. And when I specify list, everything in my code needs to either have been created in reference to the list, or reference another thing that would end the list. And that's not wholly true, like the proc.time statement. You can have functions that require no argument that work perfectly fine, but very often you're going to want at least one argument in your function. Okay? So we also have parentheses that encapsulate the code you want in the function. Okay, so now we're actually going to do another minimum maximum function. So minimum, just like we had before, is equal to the mean by default, which of course will be saying the actual maximum and minimum as the for loop sees fit. So for I in list, and I really regret using the word list. Because what I really am giving it is effectively not a list. So minimum equal to I. If I is greater than the current maximum, maximum equal to I. Okay. So we have two options now. We could use the return function that tells R very explicitly what to return as output of the function. Or we can simply write a statement like this, and R will take the last thing that we write that would normally be printed to console at the output. Either one would work. I'll go ahead and do it both ways to prove my point. But I would highly recommend using the return function. It makes it a lot more clear what you're doing, and it can really prevent some errors in more complex functions. Okay, so that works fine. And return. Now, no matter what code we have at the end, it doesn't matter. Print. No, not going to do that. What do I want? Maximum times 10,000. It'll be very clear if we got the right output or the wrong output. And we got the right output. And if we don't have that there, we're going to get the very wrong output. If we don't specify return, we're going to get the maximum times 10,000. Okay? I recommend return. You don't have to, but in more complex functions, that's a very good idea. Okay? So I'm going to do another example where I just recreate a mean function. List. Okay, so we want the sum of all the numbers. We want the sample size. So n. And we're just going to do for I in list. The sum equal the sum plus whatever new element comes in, and the sample size is the number of times this for loop would run. And we want returned the sum divided by sample. And I already found a mistake I made. Okay. So I have this new and not at all improved mean function, and I made a mistake. I in left. Goodness, I keep doing that. Okay. Let's do this again. Perfect. Okay, now I need some example data to take the mean of x or norm 10. It doesn't really matter. So I'm gonna make a sort factor here. New mean of x versus the mean of x. And these values better match. What have I done? That's why you need an initialized variable and use consistent variable names. Or you end up looking silly on YouTube. Okay. And they match. Just as they should, because they're doing the exact same thing. It's just the sum of xi over n. Okay. You can also use the function to make specialized plots. One of my preferred things to do, you can embed plotting preferences in your function, and it just makes it easier to spit out consistent functions. So my plot function x comma y, those are the default arguments of the plot function, and we want them to be carried over to this new plot function title. Okay, so we haven't done this yet, but an option you have is to create default values of your argument. So until now we just said x comma y and input everything we needed, but we don't have to. You do one equal sign, and then you just set the value of what you want. So not a generic plot, comma, trust me. And new line here, x-axis equal I don't know. That worked fine, clearly. So I'm gonna do xlab. Oh no. I know why I did that. Okay, so I want x-axis, not xlab. X-axis equal independent variable. Arguments matter when you put in main equals main, xlab equals xlab, ylab equals ylab. So I changed the names of the function in my custom function to not match the default argument names in the plot function. I'm gonna go ahead and do a new line here. Y-axis equals dependent variable, and then no, I didn't get title. Okay, so that's all I have. Okay, so now that I specified argument, I need to actually put code into this function. Okay, so what I wanted it to do is plot stuff. I carry through the x comma y and main. The main is the argument in the plot function. And that is going to be equal to title, the argument I just made in my custom function. And then xlab, the argument in the plot function that gives the title to the x-axis. X-axis. And then Y lab is not the same as that for the y-axis, of course. Okay, so we have the function all made up. And that, let's run. Perfect. And here's what this does for us. I think that thing that is made and operation. Okay. Now I can have a default title, a default x-axis label, and a default y-axis label. And every time I want to use it, I just have to call my custom function. I don't have to keep typing out plot x comma y main equal not a generic plot, trust me, and so on. So if you have a plot you like, you can just keep running that plot, specifying a new x comma y or different data if you're doing a different plot. Okay, so in the next video I'm going to be talking about getting started with neural network, data cleaning, and how to build neural network architecture. And that's the end of the video. Thank you for watching.